Hey everyone, here I'm back with another fun discussion, and this time it's more fun with combinatorial arguments. So, here is a problem. It says find the number of positive integral solutions of x plus y plus z plus w equal to 20 under the following conditions, and there have been given five conditions, and all of them are separate. They are separate cases, and we need to do it like that. And here is another problem. Prove combinatorially. That is what is combinatorial argument. Giving an argument as to why it's true using combinatorics. That means by counting techniques. So at first sight, of course, these two problems would seem unrelated, but in fact, they are related. So let me just tell about this particular problem first. Prove combinatorially that R choose R plus R plus 1 choose R plus R plus 2 choose R all the way up to N choose R equals N plus 1 choose R plus 1. Yeah, before I proceed, you could pause the video and try both the problems maybe. And yeah, so the thing is that this problem is something I encountered a month ago. And I couldn't solve it on my own. I took the help of my friends and teachers, had few discussions, and finally came up with a solution. Of course, that's pretty easy a solution, but here, after a month, I came up with this problem number 11, and I solved it in such a way that it had to make use of this formula. So maybe that gave me an idea that can we use this number of positive integral solutions stuff to prove this combinatorially. Can we do that? Yeah, maybe possible. And yeah, I could do it. And that's why I've come here to share this with all of you. And let's start then with this problem. So of course, I'm going to solve only the third part here. The others are up to you. You may solve it if you're interested. But the third part was the one which I used to prove this combinatorial. So yeah, so here we need to find the positive integral solutions for this x plus y plus z plus w equals 20 such that none of them exceeds 10. None of them exceeds 10. Let's see that. So now let us see one thing that what is the number of positive integral solutions it has if this condition is not given at all. So that for that we have a formula, that is the number of non-negative integral solutions for this for an equation like this: x1 plus x2 plus all the way up to xr equals n is n plus r minus 1, choose r minus 1. And those who are interested in the proof of this may read up in several books. For example, it is there in a book called Challenge and Thrill of Pre-College Mathematics. It's a really good book for combinatorics as well. So yeah, coming back to this, now they've asked us for the positive integral solutions. If you see, zero values excluded. Zero is not allowed. So then what we can do is we can say that each one of them must at least be one, of course, because they cannot be zero and they're non-negative as well. So they have to be positive. So let's give one to all of these. And then we have given r to all of these, and still we have n minus r to give them to have the total sum to be n. So now it all becomes this. All we have changed is this n changes to n minus r. So here in this formula itself, we have n minus r plus r minus 1, choose r minus 1. So this is just an idea. This is not a mathematical proof. Of course, there is a mathematical proof. Maybe you can try it yourself. And a hint is you can choose x1 to be some y1 plus 1 And then if x1 is positive, we would have y1 to be non-negative. That's the key idea. You could do this, and just I gave an intuition as to why this is true. So this becomes n minus 1, choose r minus 1. Right. So then we have x plus y plus z plus w equal to 20. So the number of positive integral solutions is in fact 20 minus 1, choose 4 minus 1. There are four numbers here, if you see. So then what would that be? That would be 19, choose 3. That's the overall number of integral solutions this has. So then what's next? So the next thing is going to be cases, we'll take cases where at least one of them does exceed 10. So one thing we need to notice is that if two numbers exceed 10, then their sum exceeds 20. And first of all, the sum can be at most 20. So at a time, only one variable can be exceeding 10. So let us say that variable is x. So if we say that the variable x exceeds 10, then we have x equals to 11, one case. So then if x equals 11, we have y plus z plus w equals 9. And they still have to be non-negative. So what's the number of integral solutions this has? N minus 1, choose r minus 1. Here n is 9 and r is 3. So it's 9 minus 1, choose 3 minus 1. And that gives us 8, choose 2. What about when x equals 12? We would have y plus z plus w equals 8. And then this would be 8 minus 1, choose 3 minus 1, that is 7, choose 2. And then we go all the way, x equals, say, 16, then we would have y plus z plus w equal to 4. Then we would have 4 minus 1, choose 3 minus 1, that would be 3, choose 2. And x equals 17, y plus z plus w equal to 3, and then we would have 3 minus 1, choose 3 minus 1, that is 2, choose 2. So I stop here. Of course, because if x is 18, then y plus z plus w is 2. And the minimum value of each one of them is 3. So there's some must at least be 3. So we have to stop at x equals 17. So now, what these are the overall cases where this condition is failed. Which condition? None of them exceeds 10. So here we have this, which fails our condition. I'm writing for fails. This is important. Let me choose a different color to write fails, because it's important. Which fails, what's that? 2 choose 2, plus 3 choose 2, plus all the way up to 7 choose 2, plus 8 choose 2. That's nice. And I assume that x is exceeding 10. Similarly, y can exceed 10, z can exceed 10, even w can exceed 10. So I have to count 4 times this, because there are 4 such cases and they're all symmetric cases. So it would be 4 times this. Now, I wondered, how can I evaluate this? Yeah, I remembered one thing. That problem which I confronted a month ago. This, yeah, this. Can you see the similarity between that formula and this? Of course, yes. That's the key thing. So why are these formulas related? Because if you put r equals 2 here and n equals 8, you see that it's 2 choose 2 plus 3 choose 2 plus 4 choose 2 all the way up to 8 choose 2. And that's what we need. And that would be 8 plus 1, choose 2 plus 1, and that's 9 choose 3. Yeah, we have 9 choose 3. So this is 4 times 9 choose 3. And so our final answer would be this. So we have 19 choose 3 to be the overall one, and minus the failed ones, 4 times 9 choose 3 would give us success. So that's the word in bold, success. So these are the number of cases. 19 choose 3 minus 4 times 9 choose 3. So that will give you the answer. You can evaluate it. You can try that. But now I got an idea that maybe that formula, which I just used now, can be proven using this number of integral solutions thing. So that's the idea I got. And so let us do that. Yes, let us do that. So we would have, let us consider this x1 plus x2 plus all the way up to plus xr equals n. And we just derived that the number of positive integral solutions for this is going to be n minus 1, choose r minus 1, positive integral solutions. Yes. And now we divide this into cases, usually in combinatorial arguments. Since they have given r choose r plus r plus 1 choose r and so on, it's a plus, which means they've divided the problem into cases. That's the hint we can get. And we can proceed in that way. So let us take cases. So let us say x1 is 1, because it can't be 0, can't be 0. x2 plus x3 is all the way up to xr. Why it cannot be 0 is because this is the fact positive. Yeah. So then this is n minus 1. So what's the number of integral solutions for this? It's going to be n minus 1, this minus 1, choose r minus 1. And note the way it is used here. It's just the same formula. Here n is replaced by n minus 1. Sorry, there's a mistake in this. Since there are r minus 1 elements here, it should be r minus 1 minus 1. This is r minus 1 minus 1. So there are r minus 1 elements. So it's n minus 1 minus 1. Choose r minus 1 minus 1. That's the number of positive integral solutions. The same idea. So that's going to be n minus 2. Choose r minus 2. And now the second case would be when x1 is 2. That would give us x2 plus x3 plus all the way up to xr is in fact n minus 2. So this would in fact be n minus 2 minus 1. Choose r minus 1 minus 1. Still there are r minus 1 elements. So this is going to be n minus 3. Choose r minus 2. And till where can this go to? Let us see. So of course, let us take x1, if possible, to be n minus r plus 1. Then what would this be? X2 plus x3 all the way up to xr. That would in fact be n minus n minus r plus 1. And that is going to give us r minus 1. But the thing is, this has to be at least r minus 1. So each one of them would be 1 then. x2 equals 1, x3 equals 1, all the way up to xr equals 1, then the sum would be r minus 1. So if I increase x1 by another, then the sum would reduce by 1. So that would lead us to a contradiction because it has to be at least r minus 1. But if x1 is n minus r plus 2, the sum would be r minus 2, which is a contradiction. So all we need to do is just evaluate this till n minus r plus 1. So this is done. So until n minus r plus 1. So if x1 is n minus r plus 1, we just now found that this x2 plus x3 all the way up to xr gives us r minus 1. So the number of positive integral solutions is going to be n minus r plus 1, choose r minus 1 minus 1. Yes, right. There's a minus 1 as well here because it's n minus 1, choose r minus 1. Here it's n minus r plus 1 minus 1. So what is this? This is in fact going to be n minus n plus r minus 1. So it's going to be r minus 2, choose r minus 2. So yeah, that's r minus 2, choose r minus. Yeah, it's r minus 2, choose r minus 2. So why it's r minus 2, choose r minus 2 can be explained in a better way. I'm sorry for that. Uh, so take this r minus 1 and subtract 1. And there are r minus 1 here, r minus 1 and subtract 1. So it's r minus 2, choose r minus 2. Yeah. So now let's add all these cases. What we get is r minus 2, choose r minus 2 plus, if you evaluate it for n minus r, you can do it yourself. I'm sure this would give us actually r minus 1, choose r minus 2. So this would give us r minus 1, choose r minus 2, and all the way up to, till where did we do it? Till this n minus 2, choose r minus 2 plus n minus 2, choose r minus 2. That gives us the total number of positive integral solutions, because this covers all the possible cases of x1 and does the rest other. So that would equal n minus 1, choose r minus 1. We are very close, and actually we are almost done. So replace, the next step is do this, that's all. Replace r minus 2 by r, because if it's true for r minus 2, it's obviously true for r as well. Here, just substituting r as r plus 2, you get that. So replace r minus 2 by r, and also replace n minus 2 by n. So what do we get? So this becomes r, choose r, and this becomes actually r plus 1, choose r, because it becomes, this can be written as r minus 2 plus 1, and this becomes r, this becomes r, so it's r plus 1, choose r. And this, and n minus 2 becomes n, r minus 2 becomes r. So this can be written as n minus 2 plus 1, choose r minus 2 plus 1, because minus 1 is minus 2 plus 1. We replace n minus 2 by n, so it becomes n, and r minus 2 by r, so it's n plus 1, choose r plus 1. And here is that formula. We have proved it by a combinatorial argument, by the number of positive integral solutions of x1 plus x2 plus all the way up to xr equals n, dividing it into cases and finding the number of positive integral solutions for the rest. And the total was n minus 1, choose r minus 1. We equated it and we got the combinatorial argument as to why this formula, which I'm highlighting, sorry, which I'm putting a box here, this formula we derived using the idea of combinatorial arguments. So another good exercise for those of you who are interested, try to derive this in another way, not using the positive integral solutions, but use the number of non-negative integral solutions. You will get the same kind of an expression, but a bit more effort is needed, but I'm sure you can do it. So the thing is, instead of considering the number of positive integral solutions, you could try by considering the number of non-negative integral solutions, and you would reach this expression. So yeah, this was it in the video. We had more fun with combinatorial arguments. That was the title. And yeah, combinatorial arguments is like this. It strengthens your concepts and problem solving skills in combinatorics. And whoever is interested in math, combinatorics is a very huge topic. There, there are many sources of problems. There are very interesting ones like these, which I am practicing as well. So yeah, this was it in the video. I hope you enjoyed this. Thank you for your patient hearing, and I'll be posting new videos like this. We can have fun discussing math because math is just amazing, and all of us do like it. I hope those of you who are seeing this video. Thank you. And yeah, I'll be back with new videos, more topics, and all that. Thank you once again.